Are you ready now?
Yeah,
Perfect.
sure.
All right. So it's a pleasure to announce our second speaker today, Zhenjie Ren from University Paris Dauphine, who will talk about mean field optimization regularized by Fisher's information. Please.
Yeah, thank you. Thanks, David and Aja, for the warm introduction and invitation, of course. So today, it's my pleasure to talk in this probability seminar. Our recent research on the mean field optimization problem regularized by the so-called Fisher information. Well, this is a joint work with Giovanni, Julien, and Sombo in Paris. Well, it's ongoing work, but it should appear on arXiv by next month, I think. Well, let's see. So first, let's talk about the motivation. So for us, the initial motivation, at least, it comes from the deep learning. Nowadays everybody know what is a deep neural networks. So simply speaking, it's just a particular parameterization for desired function. So given a target function f, which is continuous on a compact set, let's say, and the so-called neural network is a parameterization in this form. It's a composition of activation function phi. Okay, on each layer, the activation function is in this form, a linear combination of a nonlinear function of another linear combination. Well, everybody knows that. So the universal representation theorem claims if this activation function is assumed to be non-constant, bounded, and continuous, then any continuous function on complex support can be approximated in this way. So this ensures the expressiveness of a neural network. However, why this kind of parameterization can be trained, can be approximated, it's still a mystery in mathematics, because, well, as we will see later soon, in fact, we are facing an over-parameterized non-convex optimization, which in general should not be so easy to solve mathematically. So, well, throughout the talk, we will only talk about the so-called two-layer network, or you can call it a one hidden network. So one hidden network means there's only one activation phi. There's no composition. Okay. All right. So to find those optimal ways of the neural nets, CK, AK, and BK, you need to solve this kind of optimization problem. Well, as you can see, because this function phi is nonlinear, in particular, you can choose the ReLU activation function or sigmoid, their own very irregular function. So this is a non-convex optimization and with a lot of parameters, so it's difficult to solve. So, well, in previous work and in the literature, in fact, the trick is to, well, you can add this normalization, and then you treat this empirical sum as an approximation of a new mathematical expectation of random variable CAB, capital CAB. So now once you rewrite the optimization in the probability measure space, this problem become convex. So this objective function, capital F, is a function defined on the probability measure space, and it's convex. It's just a quadratic. Okay, so now we are facing this convex mean field optimizing problem, inspired by the neural network problem. So in order to solve this kind of convex mean field optimization problem, we need to, well, first let's review some literature. In the previous work with Taiton, David, and Lucas, so we add a regularizer to this mean field optimization problem, which is a relative entropy denoted by H in the slide. Sigma is temperature, usually taken to be small number. Okay, and we relate this regularized by entropy, regularized mean field optimization problem to the so-called mean field Langevin diffusion written here. So here the DMF is not introduced, but we will see it later. It's an intrinsic derivative of a function defined on the probability measure space, and we prove that the marginal law of this mean field Langevin diffusion, this marginal law of diffusion, converge to the unique minimizer of the regularized mean field optimization problem. Okay, so in this talk, we will change the angle of our research. So instead of adding the relative entropy, we use the Fisher information as the regularizer. So Fisher information written in this red term. So we will see by changing this regularizer, it will also change, of course, the dynamic which approximates the minimizer. And we will see how it will dramatically change the whole story. Okay, so for people who are in other community, like in closer to quantum mechanics, so the Fisher information is nothing but the kinetic energy in the literature of quantum mechanics. So if we look at the square root of the probability, namely the wave function, then the gradient of the wave function square integral is the so-called kinetic energy. Okay, so well, here is the side mark. In fact, the Fisher information as relative entropy, they are strictly convex functional on the probability measure space. And if we assume, as we introduced in the example of machine learning, F is convex itself, then as a sum F sigma, the so-called free energy function is strictly convex functional on the probability measure space. All right, so that's the regularized mean field optimization problem we should study in this talk. Okay, so the first step to understand this kind of minimization is to characterize the minimizer of this kind of function of probability measures. So let f be such a function. And first, let's define the so-called linear derivative. So denoted by delta f over delta m. So, it's defined in this fashion. So basically, we can say that we define the function which satisfies the Taylor expansion on the probability measure space to be its derivative, linear derivative. Okay, we will see examples. So here is an abstract definition. We can see example, it's more clear. So the first example, if f is linear, it's just a linear expectation of a given integrand phi. Then the linear derivative is just the integrand function itself, phi of x. Since it's linear, so in fact, you see the linear derivative does not depend on m. Okay, it's just a function of x. And in a more general example, let f be the nonlinear function g of linear expectation of phi. Then we can apply chain rule to calculate the linear derivative of this kind of f. It's just taking derivative of g, and then times the linear derivative of the linear expectation, which is phi according to the example A. All right. So that's the definition of linear derivative, and why it's important for analyzing the minimization of convex functionals. That's because of this simple observation. So let f be convex, then it satisfies this simple inequality. We move this red one to the right-hand side, and then develop the right-hand side using the definition of linear derivative. Okay, replace it, and now let's take the limit epsilon go to 0. It gives you this inequality, and clearly sufficient for m to be the minimizer is the blue term delta f over delta m on m is equal to constant. Okay, because once it's equal to constant, since m prime and m are both probability measures, the right-hand side is cancelled, it's 0. And it's 0 for every m prime, which means m is exactly the minimizer of the functional f. Okay, so this gives the sufficient definition. Okay, by introducing linear derivative, we can characterize the minimizer in this way. So let's come back to our free energy function F sigma. Well, we record here, it's just the objective function F plus small temperature times Fisher information. Okay, first, in order to show that Fisher information is a legal regularizer, we have a little theorem saying if sigma go to 0, then the minimum of F sigma, in fact, converge to the minimum of F itself. So the regularizer does not cause bias for temperature going to 0. The next thing is, I already mentioned, so F sigma is strictly convex. So if there is a minimizer, it is unique in a certain, at least in a certain subset. All right, by some calculus of variation, we can get the first order condition for this problem. Well, let's forget about all the details. So basically, it's the same thing as what is written in the previous slides. So here, with the regularizer, instead of the simple inequality we have seen before, we have this extra blue term, and this extra blue term, in fact, comes from the calculus of variation on the Fisher information. All right. And if you assume M to be regular enough, you can simply write the blue term in this red term. Okay, simplify a little bit. So this also gives a sufficient condition. If the right-hand side, the integrand of the right-hand side is constant, then based on the same logic as I explained before, it gives a sufficient condition for M to be the minimizer. And since F sigma is strictly convex, then it must be the unique minimizer. Okay, here we introduce a useful notation, which we will come back to in the later slides. So as we say, that this term comes from variation, calculus of variation. So basically, you can take it as a derivative of the free energy function. Okay, F sigma. So we just define this notation. F sigma over delta M is equal to this term. Okay, why I say this definition? That's because, strictly speaking, this free energy function F sigma is not differentiable by our previous definition. Okay, so let's look at this first order equation. Okay. If we look at the first the equation, in fact, we can relate this minimization problem to some other interesting problems. Okay, let's take this is coming from some change of variables. So first, let's take the variable change of variable psi equal to square of m. So I mentioned it before. M is the probability measures, and the square root of probability measure in quantum mechanics is a wave function. And if we look at what the wave function satisfy here, it's in fact the Schrödinger equation, the mean field Schrödinger equation. The minimizer, if m star is the minimizer according to the first order equation, and phi star, the square root of m star, should satisfy this eigenvalue problem of mean field Schrödinger operator. And well, in the simple case, if f is linear, it's our example A, if you remember. Then this goes back to the classical quantum mechanics. C is the smallest eigenvalue of the Schrödinger operator, and psi is the so-called ground state. And in general, if F is not linear, then this is a problem to find the ground state for nonlinear Schrödinger equation, which is a practical problem in quantum chemistry, for example. So, in fact, we can treat this as our second motivation instead of the neural networks. So another interesting change of variable comes here. So if we define u to be minus log of m, Okay, and in fact, we can we observe that you satisfy this ergodic HJB equation, Hamilton-Jacobi-Bellman equation. And if people are familiar with this literature of mean field game, then in fact this HJB equation characterize the value function, well, characterize the optimal control of the potential ergodic mean field game. Okay, so by these two change of variable, you can relate this mean field optimization problem to these two interesting problems. So that's a side mark. So now let's introduce the dynamic which approximates the minimizer of our mean field optimization problem regularized by Fisher information. So again, let's look at the first order equation. If m star is the optimizer, then phi star defined as the square root of m star satisfy this Schrodinger eigenvalue problem. And based on this static problem, we introduce a dynamic version and call it mean field Schrodinger dynamics. So basically, we add dt phi here. And well, a little remark is that, well, I didn't mention before. In fact, the linear derivative is defined up to a constant, but here, well, by defining the equation in this way, it's no longer up to a constant. But well, it's not so important in this talk. We are going to show that the solution phi t should converge to the optimizer phi star. That's our objective, one of our objective. So we come back to this change of variable. We define mt, which is a phi t square, and in fact, the flow mt satisfies this so-called Fock-Planck equation. Fock-Planck equation, for people familiar with stochastic process, then you can treat it as a marginal law, MT. You can treat MT as the marginal law of a mean field Burson depth diffusion, which is depth rate, which is in the bracket. Okay, we will come back to this point of view later. So by some simple calculus, we can rewrite this equation in this way. And recall this red term is the notation we introduced in the slides of first order condition, the so-called linear derivative of f sigma of the free energy function. Okay, so the Fock-Planck equation can be simply written as dtm equal to minus linear derivative times m. Okay, keep this in mind. Well, let's forget about this. On the other hand, if we recall the other change of variable u equal to minus log m, then this dynamic version is this dynamic version of u also satisfied HJB equation. Well, it's no longer ergodic HJB equation; it's a dynamic HJB equation, parabolic HJB equation. So well, you can see these three equations, Schrodinger operators, Fock-Planck equation, and the HJB equation are one-to-one to each other, like a trinity. So we will exploit this. So the first thing before studying the limit is the Wellposedness of this equation, of this mean field equation. All right, so since these three equations are the same, one-to-one to each other, so we only need to pick one, the favorite one to study. So let's pick the mean field HJB equation and prove its Wellposedness. Okay, to prove the Wellposedness of this kind of mean field equation, you only need to prove the fixed point is a contraction here. So given m bar here, you plug it into this HJB equation, which will be a classical HJB equation. and then define a function as a solution U to this classical HGB equation, and now define a new probability measure M using this potential U. Okay, and this gives you the fixed point mapping M from M bar to M. And once you prove this mapping admits, well, is a contraction, admits a unique fixed point, then you prove the mean field HGB equation is well posed. And in particular, you only need to prove for this contraction on a short horizon, then you can paste the solution to longer horizon. So to show it, it's what strategy is classical, just to estimate. So first, you use some stability estimate. It's not difficult to prove that the difference between the gradient of U can be dominated by constant times the Wasserstein distance between these two given flow, M bar and M bar prime. Okay, this is stability analysis. And the second thing is more original here. So in fact, using reflection coupling argument, we may prove that for M and the corresponding M prime, the Wasserstein 1 distance between MT and M prime T can be dominated by the L infinity norm of the gradient of the potential. Okay, gradient of potential. So U is the potential of M, and U prime is the potential of M prime. Okay. So once you have these two estimates, you combine these two, you get that the Wasserstein distance between the new probability M and M prime is dominated by constant times the Wasserstein 1 distance between the input probability flow M bar and M bar prime. And since the constant depend on T, in particular when capital T goes to 0, it goes to 0. So when T is small enough, you get a contraction in this sense. All right. So this is about the well-posedness, and in addition, we can in fact have more important result about regularities. Again, look at this mean field HGB equation. Okay, so here we already solved this fixed point problem. Now we want to look into the regularity of this equation. Well, as an assumption, a very important assumption, we assume in this paper the linear derivative of delta of f can be decomposed in two parts, capital G and small g. Small g is only a real function. Capital G has mean field dependence, and we assume that the part with mean field dependence is uniform Lipschitz in X, and the real part, small g, you can treat it as a physical confinement. It is strictly convex. Okay, it has a lower bound. Well, small c here is strictly positive. Okay, so it's strictly convex, and well, also the Hessian has upper bound too. Well, using a probabilistic argument, in particular, we use the techniques in forward-backward SDE and the reflection coupling. We can prove that the solution to this HGB equation also conserve this kind of decomposition. So, namely, U can be decomposed into two parts, W and V, where W is Lipschitz as the capital G, and V is convex, strictly convex as the little g. Okay, and moreover, these coefficients, Lipschitz coefficients and the convexity, the Hessian bonds, C and the capital C, they all do not depend on time. So we have uniform in time estimate on those regularities. So this will play a crucial role in the later analysis. But I will not go to detail. I just tell you the result. So in order to prove the convergence of this so-called mean field Schrödinger dynamics towards the minimizer of the mean field optimization problem regularize the Fisher information, one key observation is the following energy dynamic. So F sigma is the free energy function. Well, it's F itself plus Fisher information regularizer. Once we plug in MT, the marginal law of the mean field Schrödinger dynamics, then we can compute the time derivative of the free energy. In fact, it's explicitly written in this way. Why it's so? In fact, it's very easy to see it formally. Well, to compute the time derivative of free energy, formally it's just equal to this because of the definition of linear derivative. Okay, because linear derivative means the difference between the functional value can be written as the integral of linear derivative times the difference between the measures, and difference between the measures in small time, it's just the dt of mt, right? And now you develop dt of mt using the Fock-Planck equation we have introduced before, and using our notation of delta F sigma of delta M. We recall that the Fock-Planck equation can be simply written in this way. And this already gave you the result. So that's why I say formally it's very easy to obtain. To prove it rigorously, we rely on exactly the regularity results we have shown before in the previous slides. Okay. And this intuitively, in fact, already gave you the convergence result. Why? That's because we recall that the first order condition for M star to be the minimizer is this linear derivative of free energy function equal to 0. Okay, this is sufficient condition. And if you look at this energy dynamics, it says that along the mean field Schrödinger dynamics, the energy always decrease at this speed, and that is it will always decrease until the speed touch 0, right? And once the speed touches 0, you evoke the first order condition. You touch the minimizer. Okay, so that's the spirit, that's the intuition behind the proof, and the result says, well, here I don't show the real proof. It's a little bit technical, but eventually we can follow this intuition and prove that the marginal law of the mean field Schrödinger dynamics MT really converge to the minimizer M star in the sense of in the sense of Washington 1. Okay, and in fact we can do much better. We can prove the exponential convergence. Using the convexity of F, the Poincare inequality, and the regularity estimator I showed before, we can prove this kind of inequalities. So in fact, the rate of the decrement of energy dominate the constant times the difference between the current energy and the minimal energy, because we already proved M infinity is M star, if you remember. Okay, and well, this gives you the exponential convergence by ground wall inequality, as you can see, and the convergence rate is C. And this constant C depends on the coefficient of Poincare inequality and the estimate we have for we have obtained for the regularities. So till now we have proved the mean field Schrödinger dynamics converge to the mean field optimization problem regularized by the Fisher information. Okay, so it offer an approximation to the minimizer, but in fact you can construct infinite number of stochastic processes which approximate this kind of target measure. Why this mean field Schrödinger dynamics is optimal in certain sense. That draw us to the study of gradient flow. Okay, so let's recall what is gradient flow. let's first record the basic case in the Euclidean space. So in the Euclidean space, we know that the gradient flow is expressed in this ODE, right? So F is the potential, is the landscape, then gradient flow should look in this way. And what is it? So we can in fact write it in another way. So let's first expand the implicit Euler scheme for this continuous time dynamics. And the Euler scheme, the implicit Euler scheme can be read as a variational problem. Okay, in fact, given x at time I, you can solve a variational problem to get to the value of x at time I plus 1 with time step h. Okay. So this is a so-called variational formulation for the gradient flow. And we also recall the similar work of JKO for the gradient flow on the probability measure space or on the Western 2 space, let's say, Western 2 space. So given a function of probability measure f, okay, we can define a similar variational problem to determine a gradient flow. All right, and what is interesting is when you, well, here, sorry, let's be more precise. So, so here, instead of the Euclid distance, you replace it by Western 2 distance. Okay, and what makes the story more interesting is when you add the entropy as the regularizer. Okay, you add the entropy as a regularizer to this objective function, this potential function f. Then the JKO paper tells us this discrete time flow MH will converge to a continuous time flow, which solve this Fock-Planck equation. And as we all know, this Fock-Planck equation is indeed the marginal law of the mean field Langevin dynamics. So that's why the Langevin dynamics is interesting itself, right? It's a gradient flow for functional regularized by relative entropy in the Washington 2 space. So here in fact we have a similar story for the mean field Schrödinger dynamics. So what we should do is replace. So there are two replacements. Let's see. First, we will replace the metric of the space. So here we have W2 space distance. Replace W2 distance by the relative entropy. Okay, or well, more precisely, it's the W2 squared by relative entropy. Okay, and then we also replace the regularizer, the previous regularizer relative entropy by the new regularizer Fisher information. So after these two replacement, we define, in fact, we are trying to define the gradient flow of this regularized potential in the space measured by relative entropy. Okay, and what we will get? In fact, we will get our mean field Schrödinger dynamics. And here I show it formally. So let's recall the first order equation. It says that, well, if mi plus 1 solve this mean field optimization problem, then it should solve this first order condition. And we can prove that when h go to 0, this time step goes to 0, this discrete time flow will converge to a continuous time flow n. And what's the limit? Formally, you can see that the limit should read in this way, right? Formally. And this is nothing but the mean field Schrödinger dynamics. Well, because log t dt log is equal to dtm over m, right? So that's how we get it. So this is a formal proof, but in the paper we can prove in rigorous manner. So so we have shown that the mean field shading dynamics converge to the minimizer when the problem is regularized by the Fisher information. Also, we show that this dynamics is in fact optimal in the sense of gradient flow with respect to relative entropy. So another problem which is important to complete the story is why this is useful. In other words, how can we simulate this kind of mean field shading dynamics to approximate the minimizer, right? So to make a story simple, let's introduce the numerical scheme in the linear case. So f is linear here. Okay, linear expectation of small f. Then the Fokker-Planck equation can be written this way, as we said. It describes the marginal law of a burst and death diffusion with the death rate equal to this term. Okay, equal to this term. And CT is just the regularization, is the normalization constant. So we don't need to care now, but later it will be interesting. Well, this is that is to say there is a natural diffusion behind this equation, but the problem is we do not know analytically what is this density function m. So we cannot evaluate it numerically this death rate, and this certainly cause problem for numerical simulation. So how to make a detour to this difficulty? Okay, how to make this detour? Let's again turn to the change of variable, so the square root. So phi as the square root of m should satisfy this shading operator. Or you can say imaginary time shading equation. If and this CT, sorry, this red CT is the orange CT here. It's the normalization constant to make m as a probability measure. Okay. In fact, you can introduce two scaling of this equation. Okay, you can two scaling of this equation. First scaling is to remove this normalization constant c. The second one is change this normalization constant to be the normalization constant which make psi tilde to be a probability measure. Okay, recall c is the constant which make m to be probability measure, but now I change c to be c tilde, which make psi itself to be probability measure. Okay, and well, why I call it scaling? In fact, there's a difference between phi and phi bar or phi and phi tilde is just times constant. Okay, times deterministic process. Okay, so why I introduced the two scalings? In fact, they are all numerically friendly. Okay, so for the first one, it is in fact based on Feynman-Kirk relation. We can write out the probabilistic representation of psi bar. Okay, so this one can be simply simulated numerically. And for psi tilde, it's just the marginal of burst death diffusion, and here with death rate f. So it's a previous bizarre term, gradient of log m disappeared. Okay, that's the thing which we cannot evaluate now in this formulation. It disappeared. So psi tilde become numerically accessible. So eventually, we are interested in MT. And recall that MT is the square of psi, right? And psi is just a constant different from psi bar and psi tilde. That's why you can rewrite psi square in this way. Okay, in this way. And since the psi bar can be simulated using this Feynman-Kirk representation, and the psi tilde can be sampled as the marginal law of a burst and death diffusion with simple death rate. So here xi is the sample of this Wellposedness diffusion. And after all, we can represent MT numerically as the weighted empirical measure like this, okay? And everything here is numerically accessible. So this gives you a way to simulate the so-called mean field Schrödinger dynamics, which will approximate the minimizer. So let's do a quick numerical test. So if we take the small f, well, we're still in the linear case. We take the small f, the potential, in this form, okay? So basically, the mean field Schrödinger dynamic should give us the minimizer, and which should concentrate here, right? Should concentrate here. And that's what it does, okay? After our numerical simulation, our samples are concentrated in this area. And this is training error, and it's a log training error, log training error. And we can say that indeed we have exponential convergence, okay? And why I choose this particular f, this landscape, this potential function, that's because for this kind of potential function, Langevin dynamics can never work, because Langevin dynamics only see the gradient of potential. And here the gradients in this interesting area is always 0. Okay, so for Langevin, it's blind. Langevin dynamic is blind between -5 to 5, I say. Okay, does not see the change of landscape, but Schrödinger can see it. Okay, so Langevin must fail in this case, but Schrödinger still works. Okay, so well, let me simply conclude my talk. So we studied the mean field optimization problem inspired by the study of neural network, the training of a neural network to be more precise. And in this paper, we focused on the regularization using Fisher information instead of relative entropy. And that lead us to this mean field Schrödinger dynamics. And we find that free energy always decrease along these dynamics, and the marginal law of the free of the mean field Schrödinger dynamics converge in W1 or in L1 to the minimizer exponentially quickly. And well, we also show that this dynamics is spatial in the sense that it's a gradient flow if you measure the probability measure space using relative entropy. And finally, we say that this method is also also numerically accessible, implementable by introducing this Monte-Carlo method. And I think even in the linear case, this Monte-Carlo method seems to be new to the literature. So it may have interesting application even in quantum chemistry. But well, I'm not expert in that. So if in the audience they are expert in that, I'm very interested in further discussion. So thank you very much for your attention. That's all for my presentation.
Thank you very much. Are there questions? Maybe then I can start with a more curiosity. So you motivate, I mean, I think it is a supernatural problem to look at this mean field optimization problem, but you motivated it by this fitting of neural networks. So just wondering if you can now somehow come back to this problem. So do you learn something now that you can use to understand this calibration problem or fitting problem of neural networks better?
Okay, better. I cannot say that because that's what's disappointing you a little bit. So why it's not? I cannot say better. That's because if you here I introduced the algorithm for the linear case, and eventually you see you have to do this simulation, and this simulation in fact is very efficient in linear case. Okay, if capital F is a linear, it's a linear expectation of small f. It's very efficient because in fact you only need MT for T big enough, right? So in the linear case, in fact, you don't need to evaluate the weight of this weighted empirical law. You only need to sample the marginal law of the birth and death diffusion with death rate f. You can sample it at till capital T, okay, and then at capital T, you calculate this weight once, only once for all. Then you get your MT, right?
Yeah.
So this is a very efficient algorithm. But in the nonlinear case, since in your potential, it's not simply F anymore. It's delta F over delta M. And it depends on M. So you need to compute MT for each small t. Okay, which means you need to calculate the weight for each small t to update. All right. So this will add quite much complexity to the algorithm, but it still works. Just a little bit slower.
Thank you.
Okay, but the thing is, in some particular cases, well, for example, here, that's why I mentioned this example. If the landscape is irregular, but do not need to be so irregular. It just need to be the gradient to be very big at some place, and then the gradient descent algorithm will fail because it will ignore this kind of jump into right? But this kind of birth and death driven algorithm can avoid this kind of bias. That's the advantage. And also, if we go back to the literature of content chemistry, then it's more nature to study this kind of problem.
I got another question as a private message in the chat, so let me read it to you. So the question is, Fisher information is also used as another optimization method using natural gradient. Is there any connection between using natural gradient and your method?
Using natural gradient. So let me think. Natural gradient means what? Let me think. Well, first, I don't know what does it mean. Natural gradient.
Sorry, I can also not explain the question further.
Yeah, but I'm sure it has other application, Fisher information. It's a common notion in the information theory, right?
Are there further questions?
Also ask additionals. Thanks. It relates to this basically. In terms of the information geometry, what kind of extensions is there any special logic why Fisher information here works? Could this be extended to other informational measures? And also in terms of the divergences, the Waschmidt and Wasserstein 1 and 2, could this be extended, say, to Kullback-Leibler and similar divergence measures, even Bregman, that are used in probably such optimization problems?
Okay, that's a good question. Let me think a little bit. Yes, so well, you are asking whether there's a general theory behind all those things, right? Well, it's hard to say. Well, the short answer is hard to say because you can see that in the let's go back to the beginning. In the previous work, we studied the regularizer using relative entropy, right? The KL divergence. And this leads to the Langevin dynamics, or well, more generally, the mean field Langevin dynamics. And just to replace the relative entropy by the Fisher information, that leads us to a completely different dynamics. So I don't see how you can propose a general theorem which should say that you can use different information geometry to you can combine all those geometry into a general theorem.
But maybe just is there any special logic? I mean, could this work for in general information that measures as regularization here, or is there special logic why Fisher information is key for this aspect?
Well, I can only compare the relative entropy and the Fisher information. So here, relative entropy at the end. Well, let's go back to the numerical example. You can see it more intuitively. So, as I say, the Fisher information is corresponding to the large band dynamics, which is the first order algorithm, right? It's a diffusion with drift, which is a gradient of potential. And so in other words, it's a first order algorithm. But if you look at our case, if the problem is regularized by Fisher information, then the dynamics, the Schrödinger dynamics, is in fact a zero order algorithm. It's only, you only need to evaluate the potential itself. You don't need to have access to the gradient. Okay, so by changing this information geometry, in fact, your gradient change dramatically from a first order dynamic to a zero order dynamic. So I don't know whether I answer your question.
It's clear now. Yeah. Thanks. Thanks.
Thank you.
Are there further questions? All right. It's not the case, then thank you again, Zhenjie. Very nice talk.
Thank you.
And as usual, we have a next seminar in 2 weeks from now. Thank you.